Yeah, I'm really happy to be here at Lambda Days. I wanted to come here for a very long time, and yeah, I'm finally happy that this has happened. It's a great place. Thanks for having me here. Today, I'm going to talk about type search. So a type-directed API search. And before I start, I'd just like to mention that this is actually joint work between Marc Etter and myself. Yeah, Marc used to be a master's student with me at the OST. Since this is something that a place where it's not very well known. So let me just tell you a few words. The OST is a university. It's been rebranded, like everything, like yogurt and everything. Universities rebrand themselves also. So OST used to be something else, but now it's called the OST. It's the largest university at the eastern part of Switzerland. Yeah, we also have computer science naturally. Good. But maybe some of you have known this from Zurich. So Zurich is one of the larger sort of functional programming slash PL slash Haskell conferences, get-togethers. It's been happening for this was the 9th time at the OST. We have about 450 people. I'd encourage you to come in case you want. Entrance is free. It's a nice crowd. Yeah. This year we also have NixCon that's going to take place in September at the OST. I'm also co-organizing that. So yeah, in case you are interested in these things, I think that would also be something good. But anyway, now let's come back to the topic that we want to take a look at. How many of you know something called Hoogle? Oh wow, nice. But not all of you. Great. How many of you have actually used Hoogle? Okay, that's I guess once. How many of you use it once every month? Wow, hands up. Well, why do you not use it more than once a month? Is it because you don't use Haskell? Hands up. Yeah, that's the other half of the room. Super. So after today, I guess I'll be able to help you guys with this, or at least not me, but you guys can take the ball and keep it rolling. Yeah. So for those of you who haven't used Hoogle yet, let me just give you a little quick rundown of what this is. Right. So typically, yeah, if you're a programmer, you typically don't write everything from scratch, right? No one does that. What you typically do is you want to build on the work of others, yeah, and you want to search for their libraries and stuff like that. Unfortunately, these days, what this means is that you go on Google and you type, I want to convert a string to an int, and you get some code fragment that's most probably wrong, and all that stuff happens, right? Now, what would be a world where you could actually put the function you want in there, yeah, or the type of the function you want in there, and it'll just spit out all the function signatures that would work, yeah? So let me just give you a little quick demo of what Hoogle is. By the way, Hoogle is not mine. When I looked at this, I was like, wow, it blew my mind, right? And this is one of the things that Haskell people really like, right? And Hoogle is actually by Niel Mitchell, and for a long time, it's a great system. It's there for a long time. He's changed it all over the place. Yeah. So this is the Hoogle.haskell.org, yeah. And here let's take a look, right? So let's say me as a developer, yeah, I want to have a function that I have a list of things, right? A list of names, and I want to choose the names that I don't know, have even number of characters or something like that. So the most general form of that would be I have a string. So in Haskell that's a list of chars. In general, that's a list of anything, right? So I have list of A's, I say, yeah. That's my first argument. I want a second argument. Let's say that's a function, a predicate, right? That would be a function from bool to from list to bool, right? A list to bool. And I want to get out another list of A's. Yeah. So as a program, I would say that, yeah, I want something of this type. Then I make a mistake. A predicate. I say search. I've definitely made a mistake here.
You wanted a bool, didn't you? Yes.
Yeah, you're right. Thank you very much, Phil. Thank you very much, everyone else. Yeah, thanks. Now it's there. Yeah, so I have filter, which is the first thing that it takes up, but there are more functions like this also. And this is also really cool, right? Because when you do like a Google search or something, you'll get one thing, and you think it's correct, but maybe it's not. You don't have all the possible or all the probable ones there. So this is a really nice tool. Haskellers use it a lot, right? Okay, good. So this was Hoogle. So till now everyone can put their hands up and say, okay, they've at least seen Hoogle once in their lives. Yeah, cool. Okay, so now how did all this start, right? So for a number of years, yeah, I've been going to places and I've been asking people who come to these sort of functional programming language type events, but actually do other things in their day job, yeah, and ask them, do you have something like this in Java? And every time they've said no. Right? And I was thinking, this is strange. Why hasn't anyone done this? Yeah? And then at one point, Marc, who was at that time my master's student, we were coding up something together in Java, yeah? And we were searching for some function in the normal way with Google and all that stuff and Stack Exchange, and then he said, why is there nothing like this in Java? And of course, I told him, yeah, that's because Java programmers don't deserve nice things. And and of course, students, when I talk like this, they just ignore me. But this time, Marc said that, okay, this would maybe a good master's thesis project. And I'm like, yeah, but you already have a master's thesis project. I'll tell you what, I'm really interested in this. Why don't you fail this one, and then we can redo it, and then we can. And he called my bluff. He said, yeah, let's do that. And from then on, he stopped working on his current one. I failed him. Next semester, he did this, and he got the highest grade. So it's all good. So that's how it started. Anyway, so now what are we doing? So the dream is, right, of program search, is that you have a function in your head, you write a specification down, you want to search for something like this, and your system tells you, hey, it's already been implemented, it's here. Yeah. Now all the things we do right now are approximations to this. Yeah? So currently, API search, unfortunately, is the same as web search, which is basically text-based. It may now have some AI garbage in it, but it's still basically text-based. There's nothing really symbolic, except for things we saw this morning, right? That was great also. Yeah, but what do we actually want? We actually want search based on specification. Right? And now, although our types are currently not as powerful and so on, but we could sort of get one step nearer to the specification by using these types. And types are a form of specification, formal specification. And the idea is type-based API search, which I just showed you, right? So, but it's already done. Everything is good and it's working and people use it. Yeah, it's not a new idea by any stretch of the imagination, but it's only currently possible for a few select groups of communities. Haskellers, yeah, and some other smaller places, which I'll get to later. So in 2016, yeah, I also had a student who did this work for Scala. Yeah, so it was his idea. Yeah? He came up to my predecessor at that time. I didn't have this job at that time, and he said that he'd like to do it for Scala. Yeah, and he did it for Scala. And there was a paper at Splash at that time in 2016 about this, and it was good. And he claimed also that it would be possible to extend this to multiple languages, which was valid and everything. But what he used there was the standard search-based techniques, Lucene search, these sorts of things, making a vector. It worked, yeah. It worked. It wasn't in my style, but it worked. And yeah, so 2016 we did have this for Scala. Now, when Marc got this project, right, I said that, yeah, take a look at that stuff, and if you like it, you can try to extend it. He tried to extend it. It was a lot of work, right? He had to basically redo a lot of the stuff, and the results weren't as good. And I kept on prodding him, yeah, like any good supervisor should. Said, yeah, have you looked at type theory? And he always, when I say these things, students always think, yeah, whatever, I have work to do. And so and at some point we reached sort of a thing where it was just getting too tedious to do anything. And I said that, yeah, let's try looking at this from the view of type theory. And successively we sort of built a system, and it was really nice, the things that came out of this. I'm going to show you some of the things now. Yeah? Okay, so what makes this new approach appealing? Yeah, so it's targeted at mainstream languages. So by mainstream, unfortunately, I have to talk about typed object-oriented languages. So you have generics, so parametric polymorphism, and you have ad hoc polymorphism and some sort of subtype polymorphism running there. Yeah, this approach is inspired by the Curry-Howard correspondence between proofs and programs. The reviews on this said that, yeah, I don't really use the Curry-Howard correspondence concretely, so I'm saying that, oh, it's inspired by this, because you could also think of this whole thing in type theory itself without proofs. So yeah, obviously it's a correspondence. So what I really liked about it is it took an ad hoc, so it went from an ad hoc way of doing things to a more general way of doing things, yeah, in which we could use the same approach for many languages that fit into this category. Yeah. So category meaning it has some things like functions, it has parametric polymorphism, ad hoc polymorphism, and some form of subtyping. Yeah. So all these things are supported. And what we really saw is that type search is actually proof search. I mean, yeah, that's the inspiration from the Curry-Howard isomorphism that we got. Yeah. And the interesting thing is, I'll maybe come to this later, is that once we did it like this, so initially it was just, the idea was that let's try to make this as elegant as possible. I don't want so special rules in this sort of search vector space to do anything. I want to have something generic using proof rules, right? And let's try to build a proof out of this. And once we did it like this, so Marc sort of just stumbled upon this thing that he just said that, yeah, one day he said that, yeah, you know, I sort of stopped this upper bound. I said, so normally we do a timeout, right? We don't do this forever because it's going to keep on generating proofs. He said that when I sort of took out this timeout, strangely enough, I didn't just get single functions as a result of this search, but I got combinations of functions. And I'm thinking, oh yeah, of course, yeah, because a proof, you can either use one hypothesis, which is your single case, or you can use a proof that sort of combines hypothesis together with implication and get another proof. So basically, it just sort of rolled out, this program synthesis just rolled out of this approach, which was particularly very interesting to see. Yeah, and sort of reaffirm my belief that trying to get an elegant solution out of things is the best way to go forward. Anyway, so let's talk about what's happening. So I'll start with a general overview of the architecture of the system, how this is done, right? And then I'll go into the proof. I'll show you the proof rules, and I'll show you 2 sample proofs of things that we've done now. Okay. Good. So, general overview. Yeah, so what's happening? So we have, in the beginning, you have your API source. For Java, this would be the collection of Java docs. Yeah. Then we do something called source extraction. So what we do is that we sort of read that and we translate it into sort of a general format. And this general format is basically a subset of type theory. So it's got for all, implies, things like that in there, right? And so we get a search database. It's basically the API source. So these are just the signatures, right? But we have this in our sort of special format language, yeah? Which is basically just a subset of type theory. Good, and this is all done before the user actually even touches anything. Yeah, this is all done before, like pre-processed. Then the user comes along, he says, or she says, oh, I want to do this. I have this query. The query also has to be in the same sort of language. And what happens then is that we have this proof search, which I'll show you shortly, at least theoretically, how it works. The proof takes this query and the search database and does a proof search. With the view of proof, the query is the goal you want to prove, and the search database is the set of hypotheses that you need. If you're aware of this correspondence. And so it does this proof search, and it comes up with a number of proof trees. Yeah. They are ranked, so typically this should happen together because I want the proof trees in the order that are nice, right? I don't want to have, because the proof trees can be potentially infinite, and I don't want to then select it afterwards. So it has to be some sort of laziness happening there. And so there's some ranking happening, and then I get the search results out of it. So that's basically what it works. Very simple. Any questions till now? Okay, cool. Let me continue then. Okay, so this is pre-processing, and this is the search implementation itself. These two things are the input-output that you see on the web page at the end. What's interesting now is if you take a look at each one of these little components, yeah, try to think, what is the language-specific part of this? Yeah? And it turns out, yeah, the only two things that are language-specific, like for Java, TypeScript, C#, whatever you have, are these API source, obviously, right? And the source is extraction. Everything else is standard. So you don't have to write this again. Yeah, and this is just a mapping from language to language. Yeah. Okay. So now, how do we? What does this language look like that we've used to sort of model all this this whole sort of type approach to this? Okay. So let's do this with some examples. Yeah. Say we're taking Java at the moment. Say that we have this. I have a Java method toString in the class integer. This type signature for this in our representation would look like this. It's a function from integer to string, yeah, and its name is integer hash to string. It's some encoding of this name in this sort of class space. This is a static method. No, it's not a static method. It's a member of the class. So this is the simple case. Okay, now let's go one level more. So this is something which doesn't have any parameters. So you see that the instance is inlined into the parameters. The second example is that if you have an instance method which is static and has a parameter, for example, in the string class we have value of with integer I and gives out a string. What would that be? It would be string hash value of. So this string is from, the first string is here, then hash, then value of is the name of the function, and this is a function of type integer to string, and integer is the first parameter here, and string is this output variable. So it's basically what we're trying to do is sort of have like a Haskell-like type signature of, a functional programming-like type signature of our Java classes. Yeah? Okay, what about generics? So the parametric polymorphism, what does that look like? Here we have the get method on lists. Yeah, lists have a generic type E, type of elements. Yeah, and you have the get function or the get method, which takes an int index and gives back an element, something of the element type E. And this would look like this. You have list hash get, just like before, but its type is now generic. It's parametrically polymorphic. So you have for all E dot list E arrow int arrow E. Yeah. So this is it's relatively straightforward. It's how someone who is doing functional programming would think of functions. Yeah. Okay. Any questions till now about this mapping at least? Yeah. Can you get the mic there?
I can just yell otherwise.
But I guess the people in the recording won't be able to hear this. Or is there even a recording? I don't know this.
Yeah. So how does this work for variable arity functions like printf, for example?
Printf. In this case, there would be so with variable array functions, you could treat them as individual functions then, because you're just considering the type signature, right? So if you have printf with one argument, it's a different function as printf with two arguments and so on. So you never use this variability together with another function with the same name. So yeah, you could do it like that, like how Prolog does it. Yeah. Mm-hmm. Yeah. Good. Yeah.
So it looks like this translation forgets whether or not we were dealing with a class or an interface,
Yeah.
whether we had a static method or a instance method. So does this weaken the quality of the ranking of the results?
Yes, good question. So, does this make the quality of the result? We don't know yet, right? Because currently we have no measure of the quality of the search results. This is ongoing work, so we don't know what is a good ranking. So yeah, but this is a good point to take into account when we actually do the ranking properly. Yeah, thanks for the point. Any other question? Yes, at the back there.
I have a question, because in the slides where you showed the case, the website, you could see that the arguments are separated by comma.
Yeah.
But here they're all carried away. So I have a question whether, or in the representation, do you treat them all as single argument, or
yes, yeah.
do you have a...
Thank you. Nice question. So here here I use an arrow between these elements, right? And in another case, I used a comma. This is actually an error in the slides. I should have used a comma there, right? We had this idea of should we use an arrow as in the curried form, or should we use a comma? And we said maybe it's better to use the comma because this would be sort of more in the mental framework of programmers who typically don't think in terms of currying, so we use the comma. It also has the idea that, okay, if you have a comma, it looks like a set, so these things are rearrangeable, which is actually the case here. Yeah, you're right. Thanks.
Okay, thank you.
There's a question down here and a question there.
It's become a Q&A session.
Yes, sorry.
So in Haskell, because the tool like Hoogle works particularly well in Haskell because functions are usually pure.
Yeah.
So they are what the function's behavior is to the much larger extent specified by the type, and it is less so in sort of imperative languages. So I wonder how useful this kind of search actually is in those languages if the behavior of the function is not necessarily specified fully by the type. Or
yeah, you're absolutely correct. Yeah, the behavior of the function is not specified uniquely by its type. Problem we have, yeah. We ignore all this, obviously, yeah. As do most Java programmers. No, I'm joking.
Yeah, so this is possibly a technicality, but for the final example, what I was expecting on the right-hand side was that your list would be a type class rather than a type.
You're right.
What?
Yes. So this list is currently a concrete type, and here it's an interface list. You're right. So we don't have type classes in this sort of language, right? But what we would have is subclassing that would handle this. So if I have a list here, and let's say I have integer list or something like that, or integer is a bad example, array list, for example. Yeah, that would be a subtype of list, and that we do allow. So we use subtype polymorphism to handle these sorts of things.
Okay, so when you're saying list there, that's a super type.
Yes, exactly. That's the super type of array list and blah, 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 and all those others. Yeah.
Right, but you're not, for example, forcing a class here. You're not a Java class.
No. Because for us, it's really not really relevant if I have a implementation of it yet. I'm just trying to search the. Yeah. John?
So you said that the pre-processing was language specific, but afterwards nothing was.
Nothing.
So I'm wondering what you present to the user. Does a Java user see these mangled names like integer hash 2 string, or do you render stuff using language
that's
instead?
a good question. This is something we've been sort of wrangling our brains over. What would be the best way to do this, right? And we thought that since this is language agnostic, since the technology is language agnostic, we would maybe think that the user would be willing to learn a little bit more syntax. He doesn't have to write it in Java, yeah, to get this out of it. But what he has to get out of it should be in the Java syntax so that he can find it again. And this is actually what we do. Let me go to this demo then. Let me just, now I think that's a good number of questions. I think everyone's understood what's happening. So let's take a look at the same thing in TypeSearch. This is typesearch.dev. This is let's say a working prototype of this theory. Yeah. And here we have the same thing that we did here. Here we have filter, a list, yeah, arrow. So alpha list, arrow, alpha arrow, bool, arrow, alpha list. Yeah. And now I got filter, but I also got tape while, drop while, and all that stuff. Let's do the same thing in TypeSearch. So here we have TypeSearch. It's set on Java at the moment. And I say in Java, at least, this way of doing filtering, it's done on stream. So I have stream of A's, comma, A arrow Boolean, arrow stream of A. The individual types are Java types. They have the same name. So stream corresponds to stream in Java. It doesn't correspond to list or something like that. We are faithful to the names as they are in the Java API. Yeah. So I'll just click on this. It'll type it out, and now it's just searched through it, and now it's got all these results. So also here, filter is not the first one, unfortunately. It's the second one, right? So you see here you have drop while, which takes a predicate and gives out a stream of T's. Notice also that now it's a predicate. It's not AR or Boolean. It's a predicate. So it somehow did some sort of ad hoc polymorphism magic to get this out also. Yeah? So I got filter out. But now take a look at this. We have this as it is in Java. This is sort of the Java doc template. So it's important that the user sees the stuff in his language, right? In his or her language. But it's okay if they can write this there, because this is sort of a more normalized notation of what he wants or she wants the function to do. That were the design decisions that we took. Now, does that answer your question? Yeah. Super. And you may be wondering, but is this now language agnostic? Yes, it is, because if you take a look at this thing, right, the search database also contains these snippets of what it's like in the library. So we don't do anything translating backwards and all that. It's just in the search DB. Yeah. Yeah, Pedro.
So the query is also dependent on the language a little bit, at least, right? Because Haskell, for example, don't have streams.
Yes, exactly.
Okay.
Yes, the concrete names of the types depend on the source language. Yeah, but the connectors between the types, for example, the colon or this arrow are part of type search syntax itself, and the comma. Yeah, exactly. For all is also so. Yeah, so the types are, in logic we call them uninterpreted symbols. Yeah. Yeah, up and down.
I have a question regarding when the function has like at least two parameters or something.
Yeah.
So even with Hoogle, I always struggling and say, okay, I don't know which order is it.
Yeah.
I kind of have to try twice in worst case, right? So
yeah.
Do you have any tips about it?
Yes. So this approach handles that. The order doesn't matter. Yeah, because if you look at this through the lens of Curry-Howard isomorphism, it's just modus ponens, and it doesn't matter in which order you do the hypothesis out. There's just two hypotheses in the thing. Yeah, this is solved. Cool. Nice question. Yeah.
Do I have to press something? No. How do you handle namespaces? Because you just ignore them. So if I look for stream, is it going to come up with stream that's in java.util and in java.streams and in java.collection and whatever? Or do you have a specific technique to deal with that?
It's a very, let's say, banal way we do this. Is just with this name hash. It just makes it into a string.
No, sorry, I meant in the query.
In the query. Yes, good point. So over here we can specify where we want to search. For example, here here's one, string plus Java base. So we have some way of saying restrict your query in this search space. Yeah.
I see. Thank you.
Yeah, welcome. There's one down. Kyok.
So if you're not, like in the mode when you're not doing proof search, you're just really looking for atoms.
Yeah.
You don't need, of course, modus ponens. Is there anything even special about the function arrow at that point, or do you just regard it as any other Java type constructor? Or do you need to, like, I don't know, maybe you need polarity because of the subtyping, or?
No, that's a very good question, and that's great because it leads me to the actual proof rules. We actually do need modus ponens because that's the way we make sure that the order, for example, doesn't matter. Yeah. That's cool. That takes me to the next sort of slide, right? So here are the proof rules, and there are only 5, right? Or 6. I didn't count very well. So there are only 6 proof rules here. And this is really great, right? So in the beginning, when we did this using the standard search technique, there was lots of stuff happening. Like there was this vector that we had to make, all that stuff, and it was unwieldy, right? And this is just 5 rules. It fits on a slide, right? It fits on half a slide. And so let me quickly say what these rules do, right? So we have the 2 for all rules. You can read them as for all goal or for all hype, and you can read them as type specialization or sort of making a type arbitrary and these sorts of things. Then there's actually the main proof rule, resolution resolution from proof search, right? So resolution basically this is basically modus ponens. It's like a drugged up version of modus ponens. This is the main workhorse of the proof. Then implies goal basically just says that, oh, if I'm looking for a function, then I can just free up the parameter of the function and make it a hypothesis. And then I can continue with the search with just the goal. So basically what I'm doing, how does the proof search work? If I'm looking for a function, it basically just says, take all the input parameters, put them into my hypothesis, take them that I have them available into my proof search, and then keep on doing resolution and sort of saturate the set of hypotheses, yeah? And then at some point, I will get a goal, yeah? And I'm gonna try, with unification, I'm gonna get sort of multiple instances of this goal and then give them out to the user. That's basically it, yeah. There's a question at the back.
Okay, so I'm wondering if you like try to implement some sort of structural queries over types, because I believe in Java like inheritance and like having some set of methods is like more important like feature than like querying one item.
Yeah.
And I'm wondering if you try to implement queries that will query out all the types that are inheriting certain methods with certain names, or certain types that inheriting other types, because I think that's the most crucial thing when I would come to search for anything in Java, for example, right?
Yeah, you're right. There's a little bit more going on than I show you in the proof rules, you're right. So these are the rules, this is the specification of this. But at least with subtyping, you're right. If you just make it into a big sort of set and just keep saturating the hypothesis with this, it's going to get super big. And so what we do here is we have some sort of graph structure which says that this is also that. And so it's sort of like a unifying data structure which does this. Oh, yeah. Good question. I can't keep anything from you people. This is terrible. Okay, cool. Let me go on. I have two examples that I can show you for those of you who are still thinking, is this really magic? These examples will sort of kill that idea, and then I'm just going to see what we've achieved. Yeah. Okay. So this is one example here. Yeah, I'm trying to find this a function, yeah, of type string arrow int. So I'm a programmer, and I want to get a function from string arrow int, and I actually want to parse the string and give it an int. This is a classic thing on Stack Overflow, right? How do I make a string into an int? Yeah? So how would TypeSearch go about doing it? So in its big list of hypotheses, yeah, or the library, yeah, it has, among other things, it has a function called parse. Yeah, its type is char sequence arrow int. Yeah, and typically what a user thinks is, what is this char sequence? I need something from string, but they overlook sometimes that a string is a subclass of char sequence. Right. So how does TypeSearch handle this? Yeah. Okay. So what would happen? The first thing you would have to do is to say that, yeah, okay, now instead of having the goal as some g of type string arrow int, let's just take the string, put it as one of the hypotheses there. It says, okay, instead of having a goal string arrow int g, I have the goal just g applied to g1 of type int, and this g1 is now basically the string, the name of the hypothesis string. Yeah, so I have something g1 of type string, and I need to find g applied to g1 of type int. Okay, so this is good. Now, what's happening now? Now, what I need to do in order to use this function parse, I need to somehow cast or take this string and make it into a char sequence. Since I know that all strings are also char sequences, I apply the sub rule here, and I get some other hypothesis g1 with the superscript superset whatever of type char sequence, and so I have g1 of type string, g1 blah blah of type char sequence, and now resolution can fire and says that okay, if I have this and if I have this, then I can get something of type int, and that's exactly what it did. So it says okay, I can put these two together, so I can say parse of g1 superscript blah blah is of type int. And at this point it says, I have something of type int here, and I have my goal is something of type int. Can I unify g1 with parse g1 something? And the content of g1 is the same. The superscript just tells me that, oh, I've just applied a rule there. This is just information. So basically then it'll say that, the function you're looking for, this g, is actually parse through unification. Yeah? So this is how it worked for subclassing, which is also the same mechanism we use for ad hoc polymorphism. Yeah. Okay, good. So that was one example how that worked. Yeah. And here's the second example. This is exactly the same query that I showed you in Hoogle and in TypeSearch. Yeah. And we're going to see how this proof goes on. What's special about this, what we didn't see till now, is this also has generics, so parametric polymorphism. So what's happening here? Well, first thing what happened is that we have this as the goal. G is the goal, and this is the actual query that we're seeing. So G, and this A is implicitly a for all, right? So it'll say, G is of type for all A, stream A arrow bool, arrow stream A. Yep. Okay, so there's some correspondences there. This A becomes here, and these, if you see here, these names, stream is just an uninterpreted symbol, right? Stream, Boolean becomes Boolean, this stream becomes this stream, and we have this arrow in between them. So it's not an arrow, it is, so internally it's an arrow, yeah, but in the top level concrete syntax, it's a comma, yeah? Okay, good. Everything okay? Yeah, super, great. Okay, now, what do we do now? Now we have, not only do we have an implication here, we also have a for all. So the first thing we need to do is for all elimination in logic, right? We need to say that, well, if I'm looking for something for all, if I want to prove something for all A something, yeah, what can I do? I assume that this should be true for an arbitrary but fixed A, and that's exactly what we do. So we say that, well, we choose an arbitrary but fixed A. Let's call it F because it's free and doesn't occur in this proof anymore. And so we say, okay, this G applied to this new fresh variable name F is of type stream F arrow bool, arrow stream F, and this basically it just corresponds to all these things, right? So you can throw out the for all just because you have a fresh name there. Okay, good. Then what happens now? I need something of type GF, so something GF of this type, and now I can apply basically implication introduction in order to sort of move these things into the hypothesis. I can say, I have something of type stream F, I have some function of type F arrow bool, and so on, and so I have my hypothesis. So this is exactly what happened here. This rule is called implies goal, and now I can start, so there has some correspondence here, and now I can start doing resolution, yeah, and so instantiate the for alls in my hypothesis and do resolution in order to get my stuff. So it so happens that filter will be in the set of hypothesis, yeah, filter will be in my set of hypothesis there. And so I have to somehow show you in this proof that these set of rules will hit filter, yeah? And that's what I'm going to do now. So what will happen? Filter, it's for all t, yeah. So filter is defined on any type t, and since it's for all t, I can instantiate this type with this type f, yeah. And once I instantiate it with f, I get stream f arrow predicate f comma stream f there. Yeah, that's good. And now I know that I have a function filter f of this type, yeah, and I see here that stream f, oh yeah, I have a hypothesis of this type, it's called G1, that's there. I have predicate f, I have this thing there, right? I have some sort of equality between these two things. And then from these two things, from these two things, I will get something of type stream t, and that's actually my goal. So let's see this in action. Filter f is then applied to G1 and G2. I have this type mapping in the background that says a predicate is nothing more than a function from t to bool. And yeah, that's it. These things are fixed. These I can't. These for every language I have to do it new. But currently I don't have any other way to do that. Okay, cool. And so after this, I see that I have now a hypothesis of type stream F, and my goal is also stream F, and I see that it's, in this side it's filter F, G1, G2, and here I have G, F, G1, G2, and remember the initial goal that I was looking for was G, right? So I have to do unification on these two things here, and it's apparent that the unification would result in G becoming filter, and that's the proof result that I get out at the end. So that's it. Unification, I get G is filter, and filter is included in the state result, as well as many other functions that come out of it. But I just wanted to show you that filter actually works here as well. And this is what you see in TypeSearch when we run it also. Cool. Yeah. Since I have 3 more minutes, so we've done this. It's a proof of concept. It works. Yeah. How can we improve upon this? Yeah. So currently, I said that this is just proof search, and my dream was that we'd use existing algorithms for proof search to do this, right? Unfortunately, we haven't yet done this, and I'm not sure if this is even a good thing to do, because current proof search techniques focus on finding one proof, because if you found one proof, you're done, right? But it results in like many thousands of proofs, right? Each search result is a proof. Therefore, sort of the goals are different, and I'm not sure if I can get this to work with existing proof search algorithms. One thing that we really need to do is to improve the ranking, because the ranking is actually the killer here. We want the results we want first, right, in some notion. And I think that maybe text-based search would give us some clue on this. Then it would be correct, and it would be in the rank that we sort of think would be nice. Yeah. And I would like to use a lazy algorithm for this, so that I can just pull and it'll give me the most relevant results first, and then later it'll give me the rest, right? So that's something I'd like to do. This is still ongoing work. Something else, once we get proof search working properly, it would be nice to have synthesis as well, right? This is just dropped off the truck currently, but this is something that we can actively follow then. That you said that, you're looking for this function of this type, but actually maybe you want a composition of these two functions which actually gives you this. This would be really cool. This would be something that like an LLM or something would not be, I don't want to say anything, but yeah, maybe not, at least in the correct way. Good. And of course, adding support for additional languages. Currently, we just have Java. It should work for any language. That's what we said for the Scala paper. But yeah, this should be that. So anyway, so conclusion. From this work, we've seen that type-directed API search for mainstream languages is possible. Yeah, where we mean mainstream is subtyping and polymorphism. I had this idea that there's something really wrong with adding subtyping to polymorphism together, right? But it seems like in this application, it's all okay. Well, it works quite well. Yeah. We can also do this in a systematic and language-independent way, which is something that I really think is really great for this. Key takeaways for me at this point are that specific problems, this is not the first time you're hearing this, specific problems are often best solved in the more general setting. So we did this in Lucene search with sort of vector-based methods, and it was terrible, I found. And just abstracting away from many things made the solution a lot easier. That was really great. And I would say the main takeaway from all this work would be that elegant solutions matter. People think that this is just some sort of mental game that we play, but we've seen that this has concrete implications to applicability of these solutions, to their efficiency, and all sorts of great things. Now we just got code synthesis for free. Who knows what other things would be lying unexplored in other areas of our science. Yeah, thank you. That's it for me. I don't know if there's time for questions, but thank you for the questions.
Thank you very much.
Yeah.
Okay, so maybe one quick question because the time is up, but...
I hope I didn't forget to cite someone.
That's exactly what I was going to say. But before saying that, I want to say that I want to congratulate you on getting so many questions during your talk. You were clearly communicating very well.
Thank you.
That's an excellent metric. You did really well. I also want to congratulate you on getting all your rules down to these 6 rules. That's a very compact way of presenting the essence of what you were doing.
Thank you.
And then what I want to do is harp on this thing I've harped on before, because I think developers are great at a lot of things, but they're bad at this. They're bad at utilizing our superpower, which is to build on what other people have done.
Yeah.
Right? Everything I've achieved was by building on what other people have done, and then people built on what I did. And those are the two important things, having this chain. So I think it is important in our work to stress this chain. You're very good. You mentioned Niel's work that you're building on, Niel Mitchell's work with Hoogle, but then you failed to mention the work that he was building on, which was which you don't know.
Yes, I don't know, yeah.
Right. So you're actually building on work by Bruce, Longo, and De Cosmo, published back in 1991 on type isomorphisms for Cartesian closed categories. And they gave a complete algorithm that says, okay, which types are isomorphic in a Cartesian closed category? Here are all of them. And then later that got generalized to polymorphism to system F. I think you've done something that hasn't been published before, which is generalizing this to system F sub, system F with subtyping.
Yeah.
But you want to track all that down and
yeah, you're correct. I'll come to you.
Know that. So I'll give you the citation later. But the key, A, you did a great job, and B, it's really important for all of us to make sure that we're building on top of everybody and that we know how we're doing that so we don't reinvent the wheel.
Yes, yes. Thank you very much, Phil.
All right, thanks.